Hi, how are you? Good afternoon. So if you remember the gizmos on periodic trends that I had you do, this is going to elaborate on that, okay? So I'm going to share my screen, and hopefully it works this time. So come on, yes. Okay, so periodic trends explained, all right? Like I said, you have done the activity, gizmos, and I'm not sure what is, there we go. Okay, beautiful. Finally, it's been hard to get to this spot. Periodic trends, okay? I'm going to keep this simple. And if you understand electron configurations, then hopefully this will make sense. We will talk about three. The first one we will talk about is our atomic radius, right? And as you saw in the gizmo, this is distance from the center of the atom to the outer edges of the atom, right? The radius of the atom. So you're talking about the size. When we look at the periodic table, right, we don't have to draw it perfect, but it pretty much goes like that. Let's see if we can make that a little straighter, right? It pretty much goes like that. Maybe it sticks up there, I don't know. Okay, so atomic radius. As we go across, what you learned is that the size decreases. All right? Memorize it, but you have to understand why. You need to understand why. As you go down, the size of the atom increases. Okay? Now, when we talk about these periodic trends, we're often not concerned about the noble gases. Noble gases don't really participate in bonding. They are chemically unreactive. Remember, they are inert, which means chemically unreactive. And I'm going to not have them of any concern, okay? So when the size of the atom, it gets smaller as we go across. It gets bigger as we go down, right? I'm going to draw that a different way. We could also say that it gets smaller as we go up, right? And it gets larger as we go that way. So it's the same thing, just opposite. Increase. And then over here, I'm not going to write smaller. I'm going to write decrease. Such that, and these are mostly questions you had to answer on the activity, the gizmo. We have our very small particle or atoms up here. And we have our very large size elements down here. All right, now let's talk about why. And in reading y'all's answers, a lot of you did a fabulous job, okay? Now, as we move across, okay, we know, once again, I'm gonna write it again, as we move across, the size decreases. And the question is why? Okay, well, think about it. We've got more protons in the nucleus. And you guys, that was a question, right? I've got sodium with 11, magnesium with 12, aluminum with 13, silicon 14, phosphorus 15, sulfur 16, not 17, chlorine is 17. Chlorine is 17, and then argon over here is 18. So that's a period. So notice that as we go across, our atomic number increases, so we get more protons in the nucleus, all right? So we have a greater positive nuclear charge. As we move from left to right across any period, right? All of this kind of goes together. All of this, all right? So that's the first part of why, because as we move across the period, our nucleus gets more and more positively charged, okay? The other part as to why is that the electrons, the valence electrons, for every element in a group, I said that incorrectly. For every element in the period, right, because we're talking about horizontal, and the period has the valence electrons for every element in the period are located on the same energy level. All right. And if you do not include this within your answer, then it is no longer valid. And I could explain why later. So the question is, why does the size of the atom get smaller as we move across the periodic table? And I'm going to explain it visually this time. My nucleus is +1. There's one valence electron. My nucleus is +2. Oops, let me not circle it. My nucleus is +2. There are 2 valence electrons. My nucleus is +3. There are 3 valence electrons. And notice they're all on the same energy level. My nucleus is 4+. And I have, oops, I had too many electrons. No. I lost my mind. I've got 4 valence electrons. My nucleus is 5+. I have 5 valence electrons. The nucleus is 6+. I have 6 valence electrons. My nucleus is 7+. Actually, this is actually 11, 12, 13, 14, 15, 16, 17. And I have 7 valence electrons. And then we get to argon, who is 18. Okay? So what you see is the nuclear charge, the positive nuclear charge increases, and the electrons are being placed on the same energy level. They're either on the first, if we're talking about the first period, they're on the second, if we're talking about the second, but that only changes as we go down the group. As we go across the period, the electrons are on the same energy level. So what happens is there is a greater, nope, let me go backwards. There are more protons, more protons. Therefore, remember the 3 dots being therefore, greater nuclear charge. And electrons placed on same energy level. So the attraction increases. You should be saying, if you don't know, the attraction between what? The attraction between outer, no, let's just write, yeah, between, I'm just gonna write electrons and nucleus increases. As attraction increases, the size decreases. Okay? And all of that, particularly this, isn't a good answer as to why. Okay? And most of you guys figured that out in the video. Okay. As we go down a group, we get bigger, right? Why? Well, here's my, let me get my periodic table of where it is right now. Oh, it's over here. I knew my group. Here's my hydrogen. He's 1+. He's got 1 valence. All right. Under my hydrogen is my lithium. Oops, I don't really want to put his symbol. I want to put his, however many protons are in there. He is 3+. He's got 2 energy levels. The outer's on the second. Under that is sodium, who has 3 energy levels. His valence is on that third. I'm only going to do this one more time. Under that is potassium, who's got 19 protons in the nucleus, and his valence electrons go out to the 4th energy level. Okay? So what you see, and let me focus, is up here, we said, well, we get a greater nuclear charge. We do. It goes from plus 11 to plus 12, and the size gets smaller. So you cannot say, well, I get a greater nuclear charge, so the size gets bigger. That is not the end of the story. Up here, we said we have a greater nuclear charge, and the electrons are being placed on the same energy level. Down here, we have a greater nuclear charge, but the electrons are not being placed on the same energy level. So electrons, as you move down a group on the periodic table, electrons are placed on higher energy levels, which are further from the nucleus. Okay, now they're getting further from the nucleus. And recall, it is that attraction to the nucleus that keeps those electrons in place. So as electrons get further from the nucleus, the attraction to the nucleus decreases and the size of the atom gets bigger. Okay, you just got to wrap your head around that. Gets bigger or increases. Let's write increases. This sounds better. Okay. So it's not sufficient to say it's got more protons. It's not sufficient because that argument can fail. And it's not sufficient to say, well, it's lower down. If the question is why, it's not because it's lower down. It's like, let's include atomic structure here. That satisfies our atomic radius. We get smaller as we go across because we have a greater nuclear charge and the electrons are placed on the same energy level. Thus, the attraction increases. The electrons get pulled closer in. We get bigger going down because the electrons are located on successively higher energy levels, which are further from the nucleus. The further from the nucleus, the lower the attraction. The lower the attraction, the greater the size. Okay, let's look at one more of our trends, which is ionization energy. All right, ionization energy. And this is the energy required to remove an electron. All right, to take an electron off of an atom. And think about it. What is holding the electron in place? The nucleus, right? It's that positive negative attraction. Otherwise, the electron would fly off, but he stays on the atom because he's attracted to that nucleus, that negative positive attraction. Okay. As we go across a period on the periodic table, we see an increase in the energy required to take an electron off of an atom. As we move down a group on the periodic table, we have a decrease in the amount of energy required to remove an electron from an atom. All right, ionization energy equation. Well, let's take a neutral atom, supposed to be a gas. Let's remove from it by adding energy an electron. And what we're left with is the positive magnesium ion. And technically, these are in gaseous forms. Okay, if we have something neutral and we take something negative out of it, what we're left with is something that is positive. This is an ionization energy equation. It's not a mathematical equation. It's more of a chemical nature of equation. It's an ionization energy equation. It shows what happens when we remove the electron. Okay, why is the trend what it is? Why? Well, electrons are attracted to the nucleus. Right? The closer or the smaller the atom, the closer the distance between the nucleus and the electron. Thus, the harder it is to remove. Or let's go like this. Hold on. Electrons are attracted to the nucleus. The smaller the atom, the closer the distance between the nucleus and the electron. The closer the distance, the greater the attraction, right? And the greater the ionization energy. And the more energy required to remove the electron, all right? And ideally, you could pull that out of your head on your own or understand it, all right? Chemistry is conceptual as well as mathematically based. A lot of students have a very hard time conceptualizing. I think it's because they either don't try or they genuinely have a hard time. Other students don't, and that's frustrating for some, okay? So imagine as I move across, we've already said we get smaller, right? So the energy required to remove increases because those valence electrons are getting closer to the nucleus. The closer, the greater the attraction. The greater the attraction, the more energy required to separate them. As we move down, we know that we get bigger. The further away, the less the attraction, the easier it is to separate them. All right? Just think about it. If you have kids that are really close together, it's going to be hard to separate, or friends that are really, really close together. If you're a couple and you're really, really close, it's hard to separate you. If you're a couple and you're really, really far apart, it's not as hard to separate you, to pull you apart, all right? Perfect analogy. Let's look at the last one, and it is not going to be electron affinity. I don't prefer to do that, but something more important is electro negativity. Very similar to electron affinity. This is the ability to attract an electron. The ability of an element or atom, we'll just say element, to attract an electron to itself. It could actually be electrons, okay? So the greater the electronegativity of an atom, the better it is at pulling electrons. This is actually an important, everything in here goes together. Okay, so the more electronegative, the more attracted this element is to electrons, the more it attracts them to themselves, okay? So what part of the atom attracts electrons? Remember, the protons attract the electrons, right? And the smaller the distance between the two, this is what this is all about. The smaller the distance between the two, the greater the attraction. Okay? The greater the charge, the greater the attraction. Okay? So when I go across, as I see the size of my atom getting smaller, okay, I see that the distance between the outer edges and the center, the nucleus, is less. So I have greater attractions for electrons as I move across. As I go down, right, I have atoms getting larger. The nucleus is further away from the outer edges of the atom, right? We have a greater distance. From nucleus to outer edges. Weaker attraction, therefore weaker attraction for electrons. All right, exact opposite right here. Going across, notice that you get a closer distance, right? Closer distance between nucleus and outer electrons, therefore a greater attraction. It's very similar to ionization energy. It's just one is being able to attract the electrons and very much attract them, and the other one is holding on to your electrons, thus it requires a lot of energy to remove it. Okay? So, right, we know that going across, we have a trend, and we know that atomic radius decreases, right? This is just a summary and I'm about to be finished. I know that going down, atomic radius increases. These are just trends. Radius increases. I know that going across, different color, ionization energy and electro negativity increase. Negativity increase because of the smaller size, and going down, IE, and I'm going to do EN for electronegativity, decrease due to the increase in size and the increase in distance and the weaker the attraction. Now, I think it's important to get all three of those into a good answer. Size, smaller, larger. Distance, smaller, larger. Attraction, smaller, larger. Therefore, is the trend greater or lesser? All right. We'll talk about it in class. Please write down any questions that you find confusing. All right. This is stuff you'll see. Let me see it. Bye, guys. Please ask your questions. Okay. Okay. All right. Bye.